This is the Automotive Repair Podcast Network.
Welcome everyone to yet another episode of Diagnosing the Aftermarket A to Z. I'm Matt Fanslow, and resistance is futile. That and more after a word from our sponsors, NAPA Autotech Training and Pico Technology. Let NAPA Autotech's Build-A-Tech program, like Build-A-Bear, help you turn your general technician into a moneymaker for your shop. Make them a profitable member of your team. Go to napaautotech.com for more details. Are you chasing elusive automotive problems? Pico Technology empowers you to see what's really happening. Pinpoint faults in sensors, wiring, and components with unmatched accuracy. Picoscope oscilloscopes transform your diagnostic capabilities. Visit picoauto.com, that's Pico auto.com, and revolutionize your diagnostics today. All right, as you know, I get a few emails and messages with ideas for episodes or just questions in general from other episodes. And one of the questions that was sent in, it was really a conversation back and forth concerning electricity. If you guys know me that well, I struggle to talk about electricity. It's my own fault because I had to ask myself some questions. Then I tried to go answer or get answers, and things get convoluted really fast. But not going down that road. The conversation kind of went where the asker, technician, if you will, technical specialist, made a statement that I think a lot of people would agree with, except for the one hang-up word. So they said that resistance always causes current or amperage to go down. It's pretty rare we ever really get to say always or never. I can think of a few instances, but we'll be back to quantum theory and physics. And as much as I love talking about that stuff, it doesn't fit. As a general rule, though, if you see something that says always or never, it's probably wrong. Then we get into the conversation of how can it not always cause amperage to go down? Look at Ohm's law. And Ohm's law, as you know, is E divided by I times R, or voltage divided by current or amperage times resistance. So just trying to figure out current and messing with resistance with a fixed voltage, you see that no matter what, resistance goes up, current goes down. And that's a really, really important correlation. That's a really important correlation to be aware of. Even if you don't know the math, just to understand resistance goes up, current goes down most of the time, almost always. But it becomes an issue when we're dealing with things that have resistance, but not because of how they're inherently designed with like a fixed or built-in resistance, where this kind of falls apart. And it doesn't like fall apart, but where things can go a little tricky is when we're talking about electric motors. Almost specifically, I think we could also apply it to DC converters or inverters. But yeah, for the most part, we're going to stick to electric motors. I know I've said this before. I think there was an episode where I talk about looking at starter current for a relative compression test. And a kind of a weak test is to just measure the resistance of a starter motor. And it's almost a short to ground, pretty much a dead short to ground or dead short to whatever. But, it's very, very low resistance. And yet you hit the key, you get that inrush current, and you see that the current spikes something high, 1,000 amps, 600 amps, 1,200 amps, something like that, 800 amps. But it very promptly starts dropping. That's not because there's resistance built into the starter, but it's opposing current flow in the form of counter-electromotive force. So this is something that is even kind of designed into electric motors, meaning really, I think I combined that and into one word. If that goes somewhere, I'd like to get credit. But engineers consider that. They kind of build that in for control of like RPM for one reason. And that's really all that's important, is that we have counter electric motive force. That is what's resisting current flow. For the most part, when we're talking, if resistance goes up with fixed voltage, then current has to go down. And yet, with an electric motor, especially something that can draw a fair bit of current, like a starter, you can run into a situation where high resistance, and high is a really vague term, right? High resistance, what does that even mean? But unwanted resistance can cause current to go up. The RPM of the starter goes down, but the amperage goes up. Why? Well, if you've looked at anything of electric motors with your current probes or an ammeter, you'll notice that if there's some sort of a mechanical binding of that motor, be it a pump, electric pump, like a fuel pump, maybe the bushings are worn in such a way that it's restricting the ability for that motor to just turn, slows it down. Well, you know that current goes up because it has more time on those commutator segments to flow current through the brushes, at least for this conversation. So we lower the counter electromotive force, current goes up, voltage stays the same. With starters in particular, but I think we could probably see it with virtually any electric motor, just the window would be much smaller. You can get high resistance in a battery cable and have current or amperage increase. One question might be, where is that current going? And we have to think about current kind of as it relates to work. And it does, right? Like there's an equation for that. And we calculate watts. But where is that? What is the load then? What's the work being done if it's not rotating the engine? And if it's slowing that starter motor down and not turning the engine over fast and, very fast, it's not like we've built up a lot of mechanical binding holding the starter from turning. We're restricting current to it. Well, it's heat. Heat is being released, created, emanated. It could be both from the starter itself, literally cooking brushes, or the cable itself. I don't know if you've ever seen, I'm sure anybody that's worked on cars for very long, especially in the Rust Belt, you've seen battery cables when the starter's cranking over for a while cook. And I don't mean 5 minutes, 15, 20 seconds of cranking, even 10 seconds, depending on how bad they are. You'll start seeing them smoke, starting to burn, melt insulation. You'll see the cables themselves, the strands, the copper strands start to heat up and even glow red. The first time I ran into this, I didn't have a scope on the car. All I had was technically a VAT 40, but it's the snap-on version, digital. This starter's cranking over really slow. And I'm looking at the current and it's really high. I mean, we're talking it's cranking over, pulling 400 amps. Cranking amperage, I was expecting to be closer to 150 is a number. On this vehicle, it was a Chevy Suburban. Wow, it was many years ago. Cicera 1989, 90. Well, the one battery cable is braided. It's braided metal, and you can watch it go from the battery negative to the engine block, or at least one of the cables, if you will. This thing would glow red. And that's where a lot of that current was being used up, as well as the starter. NAPA Autotech training sessions are being conducted day and night in a town near you. This training caters to every level within your organization, be it a mechanical assistant, a mechanical specialist, a technology specialist, or a driver safety calibration specialist. Imagine a one-stop shop training partner in NAPA Autotech that will lead your team to a path to greatness. Autotech's entry-level Build-A-Tech classes convert the untapped potential of your new hires into money-making mechanical specialists. Autotech's higher-level tech update classes introduce specialists to the world of ever-changing technologies, which prevents your shop from getting technologically stagnant. Remember, if you're not moving forward, you're falling behind. And, turning to the front of the store, the Autotech Service Advisor class is an awesome way to hone your client advocate skill set, ultimately benefiting the customer through an improved vehicle repair experience. But it doesn't stop there. Imagine an electric vehicle class that takes your specialist well past the mundane, yet necessary safety topics. Well, it's here. Autotech's EV Ready training is a week-long curriculum that takes participants through a hands-on experience involving hybrids and electric vehicles. The session kicks off with the use of PPE and proper tooling while touching on required OSHA regulations. Then, the students dive into the lab vehicles to gain knowledge of the common high-voltage components on EV and hybrid vehicles and their function. Attendees will be taken on a path exposing them to different electric vehicle manufacturers to compare component form and location. Additionally, information about Level 1 and Level 2 charging systems will be included, along with a quick look at DC to DC charging. The operation and maintenance of subsystems are explored, including the different modes of Tesla operations, and so much more. So what are you waiting for? Commit to taking your business to the next level with NAPA Autotech training. Electric and hybrid vehicles are here, and with them, a new era of diagnostics. Don't get left behind. Pico Technologies EV diagnostic kits are your all-in-one solution to safely and efficiently service any electric or hybrid vehicle. From comprehensive high-voltage system analysis and installation testing to guided step-by-step procedures, Pico puts the power of confident repairs right at your fingertips. Future-proof your shop, boost your efficiency, and become the go-to expert for the next generation of cars. Visit picoauto.com today. That's PICOauto.com. So in this case, you have a situation where resistance goes up and current goes up. How does that play with Ohm's law? Is Ohm's law broken? I don't think so. And really, I don't think so. I know it isn't. One, it's a law, right? I can't break the law. Seriously, though, we could maybe steal a term from physics. So darn it, Matt got physics in there somehow, didn't he? And he's talking in the third person. So I got physics in there somehow. But we could steal an idea. And we could just call it like reference frame. Meaning in that very specific point in time, if we had the resistance of the circuit or the current and the voltage, we could calculate the resistance and it would be accurate. Okay. So in that specific moment in time, Ohm's law is fine. Ohm's law prevails. It's not that Ohm's law is broken. It's just we've changed some dynamics. We've kind of spread it over time, which is not where Ohm's law is going to be able to remain accurate across, anything beyond like a moment in time where there's anything changing, like dynamic. That's probably the better term, is under dynamic situations, dynamic circumstances, it won't. And a lot of equations are that way. But if we take just that moment in time, then yeah, it's fine. It survives. So really, I thought that was kind of an interesting misunderstanding that there are situations where resistance can go up and current can go up, but there's a reason for it. And if you never really thought about it, it kind of makes sense. And it's okay. When resistance gets to the point where it's fully restricting current flow to where it just can't run the starter motor, it can't exceed a certain amount of current, well, then you're going to see resistance goes up, current goes down. Okay, so there is going to be a window there of where resistance is going up, starters, or the motor at least, but in this case, we're talking the starter motor. Speed goes down, counter electromotive force reduces or goes down, current goes up, versus what we would expect with the starter rotating at a speed that we would expect, the designed speed, if you would. Yeah, I think we could use that, the more designed speed range. Current will go higher than that. So in that case, current goes up when resistance goes up, or I think more conventionally easier to process, resistance goes up, current goes up. It's not normal, not what you're going to see most of the time. When you do see it, it can be a bit of a mind job. Well, I definitely hope it explains it, but also I hope you just kind of think about that and get just that another layer of understanding, another layer, or maybe even just a slightly deeper understanding of electricity without me going into the rabbit hole that is quantum mechanics. Thank you very, very much for listening. Thank you again for the comments and the compliments, namely on the episode about pride, trying to be proud of yourself. It means a lot to know that I'm not alone, and hopefully you know that you're not alone. I guess not to, keep referring back to it, but maybe an idea or something I didn't mention during that was we all have our stuff. We all have and I really, really don't want to abuse this term. We all have our traumas. That's not to rank traumas, right? It's a spectrum. I'm not trying to say one trauma is the same as the others, but we all have certain traumas. A lot of them wildly, wildly unintentional. But as adults, they're ours to work on. They're ours to figure out. They're ours to work through. Usually it's tough to work on them alone. I'm not saying it's impossible. I'm just saying it's rough. It would be nice to remove the stigma of asking for help, getting a professional involved to help you work through that stuff. With that, I will leave you. Again, thank you so much for listening. Thank you so very much for the emails and messages. Please keep them coming. And yeah, thank you to our sponsors, NAPA Autotech Training and Pico Technology. Thank you to the Automotive Repair Podcast Network for letting me talk into one of these microphones and talk about pretty much whatever I want. I'd greatly, greatly appreciate that. I'm so very grateful for that. And until next time, take care.
You've been listening to Diagnosing the Aftermarket A to Z with Matt Fanslow on the Automotive Repair Podcast Network. Download our exclusive podcast app at automotiverepairpodcastnetwork.com because the best conversations in the industry start here. Want Matt to cover a specific topic? Check the show notes for his email. Your input matters.